Pancreas. All right, today we'll see the pancreas on the cadaver for those of you signed up for that. And remember, it's behind the stomach. It has both endocrine and exocrine functional mission both today. They both help in digestion. But it's primarily by weight, exocrine glands. Okay, I haven't talked about this before. That's why you have the pancreatic duct or main pancreatic duct. The shape is glandular. You see it looks like an inverted tobacco pipe. In our models, we model it with the duodenum. And the main pancreatic duct is that white structure right down the middle. It forks, and this is actually the one that empties into the duodenum with the bile ducts. Okay, we'll look at more pictures of that. Now, in terms of what it secretes, in terms of the exocrine pancreas, here's one already. Okay. Well, for the endocrine function, you remember studying insulin? I'll mention that again today. In terms of the exocrine function, use the pancreatic duct. Pancreatic duct. Okay, that'll empty into the duodenum. And those are the secretions, kind of a mix of those two things. So down the duct you'll get bicarbonate-rich watery juice. It'll buffer the acid that's coming from the stomach, and enzyme-rich juice. You can boil it down to those two things. Those enzymes, if you look at the slide, digest everything: lipids, proteins, carbs, nucleic acids. So I'm just kind of listing it as one term, but it has different enzymes that digest everything. Now it's about 1,200 to 1,500 ml daily. It's mostly water, like I said. It's bicarb and enzymes. And I've listed all the enzymes on this slide. However, I'll show you a picture of an example of how enzymes work in the digestive tract. I'll use proteases as an example. So pretend you have digestion that needs happening in the lumen here. So again, the principle is secrete enzymes in an inactive form and activate in the lumen. So these enzymes secrete in an inactive form. For example, trypsinogen is a protease, but that's the inactive form of the molecule. So to activate it, when you get to the lumen, there's a membrane-bound enteropeptidase within the digestive tract that will then activate it after it's been secreted into the duodenum. That's what I'm writing. A membrane-bound enteropeptidase. Okay, that is what will activate it into from trypsinogen to trypsin, and that's the active form. And then that is actually the catalyst, trypsin is, to activate other proteases, and that's what is being illustrated. I won't write the rest of them out, but that's the idea, that they're all inactive, but once you get into the lumen, one of them is activated, and it will then activate others. I'll say activate other proteases. That's all you have to know about that. So the enzymes are very effective at digesting the food you eat and not digesting the GI tract lining. Now, if you were to look at these exocrine glands under the microscope, I want you to know this, we call it this acinus structure. This picture down below. For example, you have these duct cells. Let me erase the board. Because the duct cells and the acinar cells will secrete different things. And they're stimulated by different things. New duct cells. Acinus refers to the bulbous shape of the gland. And it's the hormone CCK and secretin that will stimulate these different cells, whether it be duct or acinar cells. Well, I have secretin listed first. Basically, let's remember from yesterday, as food enters the digestive tract, the duodenum, acid will trigger the release of secretin. HCl from the stomach. That needs to be neutralized. So that is a trigger for the duodenum. That's where we are in the digestive tract. It will release the hormone secretin. In response. Now enter the bloodstream. It'll target these duct cells. And it'll make the duct cells produce a bicarb-rich juice, okay, in response. So I'll just put bicarbonate there. That's what's being secreted. That will neutralize acid. okay? So it'll neutralize the acid that's in the chyme. Remember, secretin did other things. It targeted the liver too. It helped it increase bile production. But we're just focusing on pancreas now. The other thing I have there is CCK. For example, let's say there's fat globules in the food you eat. Let's say fat. So in the duodenum, you'll release, I don't want to draw the arrow from secretin. The duodenum will release CCK. And then CCK will target these acinar cells to secrete all of those pancreatic enzymes. Okay, so then I'll just draw orange arrows. Pancreatic enzymes. Well, they'll balance the fat digestion and presumably there's other things that need to be digested. All the enzymes will digest everything, basically. So you have the acid neutralization and you have digestion of the food stuff primarily by these two hormones. They're very important. So that's kind of why I put this slide, just to remind students. The whole point of secretions is, for example, fat digestion and acid neutralization. Now, the third thing I didn't mention, in addition to secretin and CCK, which are using the pancreatic duct to get to the duodenum, is GIP is released in response to glucose. Now, if you recall, outside the acinar structure are the pancreatic islets that you've identified earlier on microscope slides. I was way at the beginning of the term. These little cluster of cells, which have the alpha, the beta cells. It's the beta cells that secrete insulin, but only in response to rising glucose levels. So if there's glucose that needs to be pulled out of the blood into the cells, glucose is a direct stimulus to get the beta cells to release insulin. If you have to review insulin on your own, go ahead. We already talked about insulin way before. It's only 7 weeks ago, but it feels like a lot longer. Go back and look at insulin if you need to. Still aren't responsible for that. So on the picture, the pancreatic islet is right here. Well, I'm going to move on to liver, the other major accessory organ of digestion, unless there's questions on pancreas. Here's some facts about the liver. It's the largest solid organ of the body, about 2% of your body weight. It's always on the right side, right below the diaphragm. It's receiving venous blood returning from the GI tract. Okay, that's basically what it's there for. Every meal you eat, anything that goes in through your mouth goes through the liver. Your vitamin supplements, your shakes, your meal, everything that's ingested goes to the liver. And so there's a hepatic portal vein that's very different from the hepatic vein. Usually when we talk about veins drain things and return it back to the heart. But this is a vein that's a portal one, and we talked about portal veins at the beginning of the course. Remember the whole cat bed 1 vein, cat bed 2? This is the same thing, okay? we have digestive tract, say, I'll draw a stretch of small intestine, and just a simple diagram. You have 21 feet and you're absorbing things all along the way as food passes. And you absorb into intestinal capillaries. Intestinal capillaries have oxygen-rich blood coming in. I'll draw kind of half red, half blue, right? I always do. Because that's where you get the gas exchange. So call these intestinal capillaries. Now normally it goes arteries, capillaries, veins, back to the heart. Okay, well this will drag, they'll all funnel into a big portal vein. Let's call it hepatic portal vein. And it goes to the liver first. So all the food you ate, maybe the green dots represent food you ate, and it's broken down and it's absorbed into the intestinal capillaries, but instead of going back to the heart, you're on your way to the liver first. So you get into the liver, and it's up to the hepatocytes to do what it does, process the food you eat, detoxify alcohol, process the fats, store glycogen, everything. And then, well, I said lighter, it's supposed to be liver, sorry. Liver. Liver does it, and then finally, hepatic veins will drain back to the vena cava. So imagine another vein going back, and it's not this long, but so this represents inferior vena cava. So again, distinguish two things. One, distinguish hepatic portal vein from hepatic vein. Because they almost sound the same. But if you misidentify them, I'm not going to give you partial credit because the function's completely different. Which one is taking blood to the liver? The portal vein. The other ones are draining blood from the liver, so that's a very different function. Okay. Remember when I taught the fetal circulation thing? I was like, oh, it's a liver bypass, and maybe you didn't understand that. Okay, you just memorized the fact. Now you can kind of appreciate it. If you don't have to process the food because mom did it for you, why do you need to filter it through the liver? Why don't you just bypass it and go straight from the umbilical cord to here? That was the whole point of teaching that prior. Okay, you can bypass the liver. Well, anyways, students always get kind of mixed up by that, so I wanted to make sure you have that diagram down. Everything goes to the liver first, right? And then you also participate in digestion by secreting bile. Okay, so this is a secretion. This is what you're receiving to process. So you receive, but you also secrete. Bile is for the emulsification of fats. Let's look at the anatomy first. I have a picture of man with his digestive viscera illustrated, so you can see liver on the right. If you remove the liver and kind of look at it from the front, if it were to be removed from the body cavity, that's what it looks like. So we have some lobes of the liver that we can identify. So that's basically the shape of it. Now you see those ligaments on the top, kind of covers it. Talked about those ligaments before. Covers the liver. It's going to kind of come in from this side too. Covers the liver. When it comes in, it forms on the front there. I won't exaggerate the bottom there, it's not that big, but well, that's the serosa, or the peritoneum, covering the liver, but it leaves a little bare area right there. Now this ligament that's been cut, that's the ligament you got to know. It's the falciform. LIG, ligament. That ligament attaches the liver to the inside of your front body wall. It's called the anterior abdominal wall. I'll just say front body wall. To the inside of your front, basically. And so you've had to cut that to kind of like, as soon as I pull the ab wall back, I know I have to cut that. Now this thing on the bottom, see how it forms a little round ligament on the bottom? Now inside there is an obliterated umbilical vein. The very one and the same as we talked about before. It's inside there. Of course, in the adult, it's not being used. I'll draw a little blood vessel in there. So that whole thing is the round ligament containing umbilical vein. Now it's also called ligamentum teres because teres means round. Yeah, so those are two ligaments you got to know. And the two lobes you got to know. The left one's a little bit smaller. Right lobe. You can see a little bit, on the right lobe, you can see a little bit of gallbladder kind of hiding underneath there. So there's nothing else to look at, basically. It's a solid organ, but that's what you can see. Well, anyways, there's a picture of the anterior abdominal wall. And I give you page numbers to look at, 154. Anterior, we rarely talk about the inside of your front body wall, but it's got that ligament. The ligament's got the blood vessel in it, the umbilical vein. So you can see how it was used when you were fetus. There it is inside there. I'm just going to run down there. Right? And coming up to meet it are two umbilical arteries. Perhaps you recall, it branches off internal iliac. And if I remember, I can show this to you on the cadaver. So basically, two come up, one vein come down, and they punch out right here. So what's the black circle? Don't think too hard. It's your belly button. Well, from the inside, right? Belly button from the inside. So that's the coolest thing you can see, the anterior abdominal wall. One umbilical, remember this? I had one umbilical vein. How many umbilical arteries? Two. I always did the 1, 2 things. So that's it right there. So we'll pull back down. So just the bottom is the round ligament. But what is it like from here to here? possible. And let's move on. Ah, underneath the liver, okay. Let's see here. That's basically what you got. So the inferior view is so we can see the other lobes of the liver. Okay, so you have a little tail lobe around here. It's called the caudate lobe. It's by the inferior vena cava. Caudate means tail. And then you have some ligaments that kind of form a portal. Kind of here, there's a round ligament there. Let me see if I can sketch that in. Anyways, this is the round ligament from the inferior view, right here. Again, you can call it round ligament or ligamentum teres. Both are acceptable. And right next to that round ligament is our other lobe, has 4 sides, quadrate lobe. And it's still, the left lobe is smaller here. Left lobe. Right lobe bigger. And right next to, on the right side, is gallbladder. Now notice the gallbladder has a duct that's going to merge with the bile duct right there. That's important. You should kind of write that in there. There's a bile duct that comes out of this opening. This is an opening, this area here. The name of the opening is the porta hepatis. This general area right here. And I want you to know that it means doorway to the liver. Things enter, exit. So this first structure that I draw, that's a secretion, is the bile duct. Bile will be secreted out to the duodenum. Okay, so that's bile duct, the first structure. And it merges with this duct from the gallbladder. So gallbladder, I'm writing here. The gallbladder, bile duct. There is the portal vein and proper hepatic artery. So I'm going to draw the arrow going in. So the blue vessel is portal vein. And I'll draw a red one for proper hepatic artery. Blood going in. Okay. So blood going in, bile coming out. The interesting thing about this is those, well, let me write proper hepatic artery under my list here. Proper hepatic artery. You haven't figured it out by now. Hepatic always refers to liver. But anyways, those are the three structures of the porta hepatis that you're supposed to know. And I think it's interesting that these two vessels are what we see in the adult circulation. But in fetal circulation, one umbilical vein accomplishes what these two vessels accomplish in an adult, right? Because the portal vein, is that oxygen-rich blood? Yes or no? I drew a blue. No. How come it's not oxygen-rich blood? Where was the gas exchange? Intestinal capillaries. So that blood is deoxygenated, but it's nutrient-rich. It's laden with all the products of nutrition. Okay. Nutrient-laden blood. But the proper hepatic artery's got the O2. So again, the one umbilical vein, it's got all that. It's got the oxygen and the nutrients. So we've got the O2, and basically that's why the blood is entering. Okay, well, great. Any questions on the anatomy? The two views we looked at? No, a lot of stuff on the board now. Moving on. Oh, I should probably throw in hepatic vein, inferior vena cava to here to remind you of that. Because I drew it before. So somewhere there's a hepatic vein draining into. So this one would be hepatic vein. And this one would be inferior vena cava. So here's some views there. Porta hepatis. I got some blank pictures for you to study. Well, let's focus on the gallbladder and what's called the biliary system. The gallbladder, it's a bladder. You know, that color is, I don't want to say it's vibrant, but it's a really strong, noticeable color. One time I was working with a cadaver, and the entire skin in this area was that color, and I thought it was some kind of mold infection, but it was under the skin. So it was like, oh, that must be the gallbladder. So it can discolor post-mortem. It colors all the organs in that area are just that color. It really does a job in terms of coloration. It can hold about that much bile. It doesn't produce the bile. The hepatocytes in the liver do, but they can be stored there. Okay, let me erase my pictures now. Yeah, hepatocytes are the cells of the liver, and we'll look at them soon. That is correct. The liver will produce about 900 ml of bile a day. Now, that's considered dilute bile. And a lot of that bile is produced in between meals. So maybe about half of that is produced in between meals. And let's see if I can get a picture in here. When you're not eating in between meals, there's no like CCK going on because you're not eating. nothing passing through here. So this sphincter will be shut. If you're producing bile and there's resistance there, you're going to like just back divert into gallbladder to be stored and concentrated. So about 450 of that 900 is diverted to gallbladder daily, in between meals. So when you actually eat, about 500 ml actually reaches the duodenum daily. Now that 500 ml will be a mix of this dilute and this concentrated bile. That 450 ml that is diverted to the gallbladder, it will be concentrated by the gallbladder. When it's in there, if you look at the inside, it has this textured surface. That'll help kind of like evaporate fluids and absorb the salts. It basically concentrates it. Okay. So this sac, it's not very big. Maybe it's like, well, you'll see it. Okay, so I don't have to tell you. You'll see it if you look at the cadaver. It's not as big as the picture looks. It's just a little bladder. Maybe like, you ever see like a regular sized deflated balloon? It'll kind of look like that, just to give you a rough idea. But anyways, the inside of it is textured. So this bile that's diverted to gallbladder is concentrated bile. And the 500 that reached the duodenum is a mix of dilute and concentrated bile. When gallstones form in there, gallbladder removal is one of the most commonest procedures. Whenever I open a cadaver, I say to myself, there's about a 50-50 shot it's there. Frequently it's not. I can't believe how often it's not there. So you're not getting the concentrated bile. You're still getting bile, just the dilute kind. So it makes fat digestion a little more difficult. But that's okay, just eat less fat. That can't hurt you. That's usually the diet that's kind of prescribed, a lower fat diet. Because fat digestion is, I don't want to say it's compromised, because you still have the liver producing bile. You just don't get that concentrated bile. Now the other ducts that are that you have to know besides the bile duct are up there. It's interesting that the gallbladder doesn't have like a valve or something. There's just this kind of spiral opening, and that kind of like is a fake valve. So things can just be diverted into it freely and it'll just kind of spiral down. And it's harder for things to get out because of the spiral nature of that groove there. Anyways, you have to know these ducts. We call it the biliary system. So let's kind of map that out. So you've got, I don't want to use green, it doesn't project very well. So basically you have, you see that at the top, right? You have right and left hepatic ducts. Know those. And they merge to form common hepatic duct. And then the cystic duct from the gallbladder will merge with that and form bile duct. Okay, that's basically what you got to know there. And on the picture, we'll actually continue on. It's the bile duct that will merge with main pancreatic duct. These two organs, liver and pancreas, are the major accessory organs of digestion. And so that's the whole major duodenal papilla thing. They kind of like, that's how they release their contents into the digestive tract there. Major duodenal papilla. I'm going to move on. So there's a picture side by side of those two drawings. And if you look at any picture or model, or picture of a model, as long as you know this anatomy, you can always orient yourself and never misidentify anything. If you can just remember this, at the gallbladder, right next to the quadrate lobe, right next to the ligamentum teres, this is the right side. The gallbladder on the right. Now, if this is the right side, what is that? Right hepatic duct, which makes that left hepatic duct, common hepatic duct, cystic duct, bile duct. They do show portal vein purple, and then proper hepatic artery red. Sometimes they show the portal vein purple, sometimes they show it blue. I've never seen it colored red. So again, now the picture is flipped, but as long as you orient yourself, you know this is the right side, because there's the gallbladder. So that makes that the right hepatic duct, left hepatic duct, common, right? Cystic, bile duct. There's the portal vein and proper hepatic artery. And you just keep going with it. There's different pictures. This one we have in the room is right there. So again, orient yourself. There's ligamentum teres. There's quadrate lobe. This is the right side. That's the gallbladder. Right hepatic duct, left hepatic duct, common hepatic duct, cystic duct, and at the tip is the bile duct. Now, what's the purple one? Yeah, you can call it portal vein or hepatic portal vein, the proper hepatic artery right there. What if I label that vein? What do you think I'm going for? Hepatic vein. Again, students always confuse the hepatic portal vein with hepatic vein. One is delivering blood, one is draining the blood from the liver to inferior vena cava. All right, let's look at the microscope of the liver lobule, or at least an illustration of what it looks like on this picture. So the liver is arranged into lobes. They're called lobules because they're microscopic. And at the center is a central vein. I use it as an example of a venule, a very small vein. And you can kind of see how they're kind of sort of hexagon in shape. Well, anyways, blood drains towards the central vein. And the hepatocytes, they process the blood as it drains towards the central vein. But they also process and secrete bile, which goes out towards the corners. And so for histology, there's not much to see except that you have these corners of the lobule, which are called portal triads, and then you have the center, which is where the central vein is. So blood is on the way out once it reaches the central vein. So you kind of have this picture. Look at the picture on the bottom. I put this picture here because I don't want you to confuse porta hepatis with portal triad. I want to draw the portal, the little liver lobule. And, well, you got central vein right in the middle. Okay, central vein right in the middle. If you can't remember which one's the central vein, just remember it's in the center. Okay, so don't make it hard on yourself. Now, on each corner, you have a portal triad, set of 3 things. What you're going to have at each corner of the lobule is a little branch of the portal vein. Okay, so this one. So we'll label this portal triad. And the blue structure is a branch of portal vein. And then the little red structure is a branch of hepatic artery, or proper hepatic artery. And then a branch of the bile duct. So those 3 things is a portal triad, not to be confused with porta hepatis. Okay, so that's that. So that's what you see there. And now, bile is draining out to the corners, but blood from 2 vessels is draining in. Okay, so what they illustrate there, I zoomed in on a part of this, so it's a little fuzzy, but there's something that you may miss if you don't look at it closely. All right, first thing is, the hepatocytes are these cells there. And notice how they're arranged in like 2 rows each. 2 rows, well, this is a good example of 2 rows. There's these structures called liver sinusoids. They're blood vessels that are going to drain to the central vein. And they're going to receive blood from the branch of portal vein and branch of proper hepatic artery. So that sinusoidal blood, called this liver sinusoid, it will be a mix of portal blood and oxygen-rich blood. So you're going to get blood that flows in there, that's oxygen-rich, and blood that flows from the sinusoid, from the portal vein into it. So I'm just trying to illustrate that both things are draining into the sinusoid. And they do try to show that, like here and here. They kind of show it somewhere on there. But anyways, the liver sinusoid, let me write it somewhere. It's blood flow toward central vein. It's a mix of blood is a mix of portal blood and oxygen-rich blood. And the reason why you have the 2 rows, no more than 2 rows, is so that each row of blood can face sinusoidal blood flow. So if you have this one, let me draw them like this. Here's my hepatocytes. Here's one row. And I'm going to draw another row like this. Oops. So those are my two rows of hepatocytes. Okay, and there's a sinusoid on either side. So that way, with two rows only, each side faces blood. And it's the basolateral membrane faces the blood flow. Let me write that down here. So I'm writing basolateral membrane faces blood flow. They even named that space right here, the space between the sinusoid and the cell membrane is called the space of Dissay. D-I-S-S-E'. So that's the space on one side. Now the apical side, the apical membrane, that's where you get the bile secretion. And the bile secretion is into a little structure called, they call it bile canaliculi. I'll say bile secretion to bile canaliculi. And that's why I drew this big space there. My understanding is that the bile canaliculi is a gap between cells on the apical side. It's not a duct. Bile canaliculi, a gap between cells, not a duct. So the bile is secreted, and it just kind of drains out to the corners, right? A gap between cells is all it is. And if you look at the illustration, it looks like it's its own separate duct, but it's not. It's supposed to be a gap between cells, that's my understanding. So these are the bile canaliculi. They're not ducts, they're gaps between cells. So that's kind of misleading the way they drew it. Well, anyways, that's sinusoid function. Okay. All the blood is draining toward the central vein, and that's where the hepatocytes have a chance to process the nutrients. You can even zone out the hepatocytes based on their location to the portal triad and the central vein. They may have slightly different functions, but we don't need to do that. The basic idea is, once you get to the central vein, that's it. The liver cannot process whatever passed by. It's on the way out. And once it gets to here, it just forms a drainage system that will eventually get to hepatic vein and then inferior vena cava. Now, in terms of the bile production, the bile salt is really the thing that can emulsify fats, which is its main function for fat digestion. And the fat digestion, we'll get to it, but basically, bile salts don't have to know the structure. And here's what you need to know. That bile salts are efficient for lipid digestion because they have a hydrophobic side and a hydrophilic side. That makes you a good fat emulsifier. So if you have a hydrophilic side, assume that these green molecules have some kind of charge, a partial charge, that allows them to interact with water. That's why it's hydrophilic. You can face water. Then the hydrophobic side can kind of face the fat. So it kind of So when you emulsify a fat in your digestive tract, you're taking that lipid droplet and you're surrounding it, forming a little globule. And the goal is to take a big fat globule and make smaller globules with the emulsification. So basically, that's all I want. There are all these details here. You don't have to know the details. Big fat globule, bile salts, smaller fat globule, maybe small enough to be digested or absorbed into lacteals. Bile salts. Emulsify fats, where I think the picture is doing a good job showing you the breaking up of fat globules into smaller droplets. Globules of fat into smaller droplets for absorption into lacteals. Remember, it's the lacteals that absorb fat, not the intestinal capillaries. True fat digestion is not fat emulsification. But what you're doing is, if you can have a smaller fat droplet, for example, large globule, and all your triglycerides are in there, enzymes can only attack and digest. My E's are supposed to represent triglycerides. So let's say it's pancreatic lipase, the enzyme that digests fat. If you have a large fat globule, you can only attack the outer molecules of fat. But if you break it up into smaller droplets, you can basically digest more of them. Okay, so that's how emulsification aids fat digestion. But true fat digestion is shown there. Okay, so let me draw the triglyceride like they do. They basically when you burn fat, this is how you do it. So you have that glycerol backbone, and you have like these fatty acid chains. Glycerol. A fatty acid is just a hydrocarbon chain. Now the goal is to break off the fatty acids so they can circulate. And so that's all the lipase does. It just breaks off fatty acids, and these are what can circulate and enter the muscle cell. So when you burn fat, these are literally what you're burning. Lipase from the liver, you have lipase activity in your muscles. So I'm just going to say, here's my free fatty acids. They're free, they're circulating. Assume they'll be used by your muscles for fuel. Enter myocyte. You can metabolize it. It's called beta oxidation. You can look that up if you want. I'm not going to teach that, but I want you to differentiate between Okay, this is a picture of fat emulsification. But when you use the lipase activity, this is true fat digestion. It's, we called it chemical digestion. This is more chemical because you're actually breaking the fat molecule up into pieces that can be metabolized by the human cell. All right, so I'm going to move away from liver, and I'm going to talk about small intestines. Any questions about the bile salts or liver? Yeah?
What does the yeast represent again? Is that pancreatic or did you say that was straight?
I'm sorry, what does what represent what?
The yeast inside of the...
Yeah, the E represents triglyceride. I drew it different over there. The E represents triglyceride in my drawing here. Here, this is a triglyceride too, just drawn differently. Any other questions? The small intestine. Liver and pancreas take a while to teach. I'm going to move on to small intestine. We talked about duodenum, first 10 inches. On the picture, well, look at the picture. Tell me what color duodenum is. Make sure you're looking here. Blue. All right. And the rest of it's jejunum ileum. Several meters, about 21 feet. It's difficult to tell where jejunum ends and ileum begins. So if a fair way to ask would be if it's close, if you can see it's close to duodenum, you know it's jejunum. Ileum I'll tag when it's close to the cecum or colon. You know you're at the end. Yeah. So ileum, jejunum, you gotta know all three parts. Duodenum, jejunum, ileum. Shown here, it's just a big coiled tube that's modified for absorption. So here it is side by side, intestines coiled in. Here they cut close to the duodenum. That's kind of where the jejunum would start. And there's where the ileum would end. And everywhere in between is just one tube, about 21 feet long. It's modified for absorption, and that's usually what I focus on. You have large circular folds that you can see with the naked eye. They're called the plica. I mentioned those before. They're circular, and they force chyme to spiral through the lumen. And then the villi are, they're going to increase the surface area by folding the mucosa. And then the microvilli are like a folding of the plasma membrane. So at every level of detail, you're having this folding to increase the absorptive area, and that's really how you're modified for absorption. Now, the small intestine, they do perform some digestion. I did mention they have brush border enzymes, so I mentioned it before. I should probably restate it here. And perform some digestion because the mucosa has these brush border enzymes. But after the duodenum, and you've been exposed to all the secretions of liver and pancreas, most of the digestion has been accomplished. And you've been through the stomach too, right? You've been chewed by the mouth. I mean, most of digestion has been accomplished. So now the main job is absorption. Oh, I say so. small intestine modified for absorption. By dramatically increasing the absorptive surface area. So you can kind of see they unrolled a piece of the wall. And I really zoomed in there on this. Let's kind of focus on this right there. So you can see how the folding occurs. So we kind of have see that shape there? That's supposed to represent the muscularis mucosa. And then you have kind of like this arrangement. So those little hills are supposed to represent the villi. It's the epithelium. But they're the villi. So what we see is we got villi. This whole thing that's sticking up is a whole fold from here to here. That whole thing is considered plica circularis. It's about a centimeter tall fold. You can see it with the naked eye. Yeah, but what you can see is that the muscularis mucosa, so deep to the muscularis mucosa is a submucosa. Loose connective tissue. But because that muscularis mucosa is all superfolded, the connective tissue of the submucosa, it's all up in there.
Is the red that's around that still muscular?
Yeah.
Okay.
So what we learn is that plica is a folding of the submucosa, all right? So you fold it all the way, get all the way up in there. Now those villi, that epithelium, deep to that will be connective tissue. I believe we called it lamina propria. Green for that. I don't want to draw it everywhere, but I'll draw it in some places, like here, where I label the villi. So what I'm drawing in green is still connective tissue, but we just called it lamina propria. Lamina propria. Well, anyways, the villi are a folding of the mucosa. Okay. Because of that lamina propria folding up into the villi. Villi, a folding of mucosa. So that's kind of why I zoomed that in. I want you to see how, at what level do you fold, basically. Okay, I'll move on. Plica, a folding of submucosa. Villi, folding of mucosa. So if you look at a few villi, you can see how they illustrate a lacteal, and we should have had intestinal capillary in there too. Yeah, we got it. Remember, you got a villi pit. Okay. I drew that before. So here's the pits. Here's the villi that stick up. And if you look at the columnar cells that line the villi, they actually have a brush border at this absorptive surface. So the shape of that cell is columnar cell, and when you look at it under the microscope, it appears like a brushed border. But that columnar shaped cell is basically, we call it a micro villi brush border. And you wrote the brush border enzymes, so guess where they are? They're along the absorptive surface. So they can finish off digestion should you need it to occur. And, well, what we see is the microvilli are a folding of the plasma membrane. Here's a picture of the brush border enzymes in work. Basically what you should notice is you're breaking the bonds at the top because you have these enzymes studded in the brush border. So by the time you get to this side, you have, for example, monosaccharide carriers to get the monomers into the bloodstream in the intestinal capillary. Here's a picture of the model we looked at before. Labeled and unlabeled, so you can study it yourself. Go back and look at your notes. I called this intestinal crypt. I called it crypts of Lieberkühn with the padded cell. I did mention that prior. And when I teach the histology today, I'll mention it again. This is on today's quiz for both groups, I think. So continue to study that for the lab practical. I've identified everything. Okay. For example, what layer is it from here and above? Mucosa. From here to here, submucosa. What's 12A and 12B? What would you call a layer? Muscularis mucosa. But you have circular oblique. You have to distinguish that. And you have myenteric plexus, this yellow submucosal plexus. You have mole. You have intestinal crypt with panicels, muscularis mucosa. What's that thing? Lacteal. You have the serosa down there. So everything you can identify here. Also, you have Brunner's glands. Brunner's glands spell brothers. Okay. Let's take a break, and we'll come back. We'll talk about the colon. Come back at 10. I just want to warn you when you come back. I'll have the gurney out. I won't open the bag. But it shouldn't smell that bad, but I want to get the gurney out so I can be good to go with the cadavers.